Kita popular en Indonesia para publicar textos.
It's 4 o'clock. Let's go ahead and get started. Or good afternoon, everyone. How's everyone doing today? Everyone have a good long weekend? Good, it's good. All right. So the plan for today is we're going to continue with our lecture notes. So we're kind of in the middle of classical optimization. And so I think we did kind of one brief example last Thursday, very simple one. And so we're going to do a couple more examples today for the single variable case, and then we'll move on to the multi-variable case. Okay. All right, so one quick announcement before we start today. It's just kind of reiterating the announcement that I said, in an email after class last week. So homework 1 originally was due today, but we weren't quite finished yet with the single variable optimization, and so I pushed the due date for that back to this Thursday. The date for that is September 7th. Okay. And so for the homeworks, I think the way most people turn in the homeworks is nowadays that they just scan their homeworks and then upload it onto Canvas. But if you want, you can also turn the homework in physically as well. And so if you have if you wrote it down on loose leaf paper, you can just give it to me on Thursday, and then I'll grade it and return it to you. Usually within a week. Usually I grade homeworks. Okay. But if you go with the online option, then you have a few more hours to do it, because I make the cutoff at 11:59 p.m. So the last minute of the day. Okay. All right, and so I think that's it for my announcements. Are there any questions I can answer before we get started for today? Everyone should be in the class now, right? So I think all the wait list, situation has kind of been figured out at this point. So okay. All right, so let's go and get started. And then what we were covering last week was a single variable classical optimization. All right, so let's start with a little bit of a review of what we covered last Thursday, right? So remember, this whole class is about optimization. So in spirit, we're going to be solving the exact same problem, or at least our objective in every optimization is going to be the same. Okay. And so in classical optimization, that's no different. And so what we're looking for are the values of the design variables that minimize some objective function. And so the symbols that we usually give for the design variables is usually X. And so for single variable optimization, there's only going to be one X. And then for multivariable optimization, we'll give them numbers. So usually X1, X2, X3. And so that's why I use the symbol X sub I there, right? And the function that we are trying to minimize is I usually label it with F. Okay. All right, and so we were in the middle of learning the classical methods. And so the classical methods of optimization, it kind of gets their name because it has their roots in kind of classical calculus and, traditional more traditional math in that way. Okay. And so using these classical methods, we have to undergo 2 steps to solve an optimization problem, both in single and multivariable, but we'll focus on single variable. And so the first step is to take the derivative of the objective function with respect to the design variable. We're going to compute the f, the x, and set it equal to 0. So in other words, we want to find the extrema, and then what's common at all the extrema is that the slope of the tangent line there is equal to 0. Hence, we compute, the first derivative, which gives us the slope of that tangent line, and we set it equal to 0. Okay. And so after setting the first derivative equal to 0, we then use that and solve for x. Then once we've determined the locations or the values of x where all the extrema take place, and so that's step 1. Step 2 is to determine whether we have a maximum, a minimum, or neither. Okay? And so it's possible to have a saddle point. Okay? And so to do that, we have to compute the higher order derivatives. At the very least, we're going to go up to second order. Okay? And so from the second order derivatives, we plug in the values of x that we found from part 1, and depending on the sign of our result, then we can determine whether it's a maximum, a minimum, or a neither. Okay, so let's do another example, just so you can see all this in action. This one's a little bit more complicated than the example we ended with last Thursday. Okay, so for this example, we want to determine the locations of all the extrema. And we're going to do it for the following function. Okay, f of x is equal to 12 x to the 5th power minus 45 x to the 4th power plus 40 x cubed plus 5. Okay. So we have a 5th order polynomial, and so our powers of x go up to 5. Then once we find the location for all the extrema, so all the values of x where the slope of this function is equal to 0, then we're going to classify these as either a maximum, a minimum, or a saddle point, which is neither a max or a min. Okay. And we're going to follow the exact same method that we have kind of up here. Okay, so we're going to take derivatives of this function, set the first derivative equal to 0, then use the higher order derivatives to determine whether it's a maximum or a min. Right. Any questions on just the kind of the recap from last time, or just the kind of the beginning of this example here? All right, so let's go ahead and get started. So let's go ahead with step 1. So first step is to find out where the extrema of this function even are. So let's take the first derivative and set it equal to 0. Take df equal to All right, so I'm just going to use the power rule on each of these terms, and so the derivative of 12x to the fifth is going to be 60 x to the fourth minus 45 x to the fourth, derivative of that, we get 45 times 4, that is 180 x cubed plus 120 x squared. Then at the very end, we have derivative of a constant. Derivative of 5 is just 0. So that's going to be our derivative. And so we're going to set all this equal to 0. All right, so now that we have the first derivative and we've set it equal to 0, now we're going to need to solve for the values of x that make this expression 0. Okay, so we're going to take this and solve for x. So let me go ahead and simplify this a little bit. So let me go ahead and factor out 60x squared. That's a common factor for all of these terms here. So we factor out 60x squared. And then inside the parentheses, what we're left with is x squared minus 3x plus 2. All right, so to make things a little bit simpler, let's go ahead and divide both sides by 60, get that out of the way. Because on the right-hand side, we have 0, so 0 divided by 60 is just 0, and so we kind of get rid of that constant factor. We have x squared minus 3x plus 2 is equal to 0. And the last thing we'll do before kind of solving for x is to factor that quadratic. So we have x squared minus 3x plus 2. So you can use the quadratic formula, to factor this guy. Or if you just kind of, if we just kind of look at it, we know this is equal to x minus 1 times x minus 2. And so our final kind of expression here is we have x squared, x minus 1, x minus 2 is equal to 0. And from this form, it's very easy for us to solve for x because we have three things multiplied by each other. And so if any of those quantities, x squared, x minus 1, x minus 2, if any of those equals 0, then it'll satisfy this expression. And so we have x squared, this is equal to 0, x minus 1 is equal to 0, and x minus 2. If any of these three expressions that I wrote here, or any of these three kind of small equations are true, it makes the above equation true as well. Okay? And so that's kind of the convenient thing of working with zeros, that it cancels out. Okay, and so from these we have three values of x. So we have x is equal to 0, x is equal to 1, and x is equal to 2. And so these three values of x, these are where our extrema are. Any questions on this? Okay, good. All right, so now that we know what the extrema are, so we have x equal to 0, 1, and 2. We don't know whether all three of these are minima. If a couple was a minima, or maybe one's a maximum, or maybe we have one that's neither. And so we need to move on to step 2. Okay. And so step 2, we're going to take higher order derivatives of this equation. Alright, so one word of caution here before we kind of move on. So, I think it's when you're kind of doing these problems, especially when you're doing a lot of these, it gets kind of tempting to kind of start from a more kind of later step, okay? But it's important to remember that when we take the second derivative, it's important that we start from this form right here for the first derivative, right? Because all these subsequent equations, right? All these subsequent equations that I've underlined here we've kind of made some simplifications due to the fact that this is equal to 0, right? But when we're taking the second order derivative, we haven't set it equal to 0 yet. And so we want to make sure that we start with kind of the most base form before we apply any simplification. And so we're going to start here. Let's go ahead and take the second order derivative of this. E squared f dx squared. But if we perform power rule on this guy again, so we have 60 times 4, we have 240 cubed minus 180 times 3, that is 54, 540 squared plus 240. All right, now that we have the second order derivative, what we can do is we can evaluate this at all of the extrema. So x is equal to 0, 1, and 2, because those are the extrema we found in step 1. And then what we're going to do is check the sign to determine whether these are a maximum, a minimum, or a saddle point, which is either. Okay. All right, so let's start. Let's actually start with x equal to 1. That's probably the easiest one to start with. And so we know from part 1 that x is equal to 1 is an extreme. So that's where the function either peaks, or it reaches a low point, or it kind of does kind of the weird saddle thing. Okay. And so what we're going to do is I'm going to plug x is equal to 1 into our second order derivative and check the sign of the result. Okay. All right, so let's go ahead and do that. So we have 240 times x cubed, and if x is equal to 1, that's going to be equal to 1 cubed minus 540 times x squared. So you have minus 540 times 1 squared plus 240 times 1. Okay. So everywhere we see x in the second order derivative, we're just going to plug in x is equal to 1. All right, and so if we plug those in, you can punch those into a calculator and you can simplify it and see. But what you should get is minus 6. And if you go back in your notes, and so if you go back to our notes from last Thursday, I didn't write it again just because it's a little bit lengthy. But remember, we're going to check the sign. Not only are we going to check the sign of the second order derivative, we have to check to make sure that our derivative order is even, which it is right now. And so since this is negative and our derivative order is even, this means that x is equal to 1 is a maximum.
Professor, what do you mean by derivative order is even? Like the second order derivative?
Exactly.
Okay.
Right. So since we're on the second order derivative, that's an even order. And so we'll have one later where we need to take a third derivative. And so a third derivative would have an odd derivative.
Okay.
Okay, so let's check x is equal to 2. And so we're gonna plug in 2 into our second order derivative above. And so we have e squared f dx squared evaluated at x is equal to 2. So what this gives us is 240 times 2 cubed minus 540 2 squared plus 240 times 2. All right, so if you plug all this in, you punch it into a calculator, you punch it into MATLAB, what you get is a positive 240. And so since this is positive, excuse me. Okay. Since this is positive and the derivative order is even, remember we're evaluating the second order derivative here, that means x is equal to 2 is a minimum. Yep.
So the minimum and maximum that we usually find out are the global minimum and maximum, right?
So these are only local, and so this
Is it local?
exactly. So right now we're only determining whether they're local minimum or local maximum. To determine if they're global, what you would then do is you would plug in x is equal to 1 back into the original function up here,
Okay.
and then find out which gives you the most minimum value. Yeah. And so for these, actually for these, because these are unbounded, unconstrained functions, what you might find is that the global minimum might be at negative infinity because it's an unbounded function. And so we're not really going to talk about global maximum or minimum just yet. But once we get to constrained optimization, probably on Thursday, then we'll kind of bring back that notion of local. Yeah. But for these criteria, these are only local extreme. Great question. Thank you for asking. Okay, and so last one we're going to check is x is equal to 0. And so we plug x is equal to 0 into into this function. Then what we have is 240 times 0 cubed minus 540, 0 squared plus 240 times 0. Okay. And so we have 0 multiplied by everything, and so that means that we get 0. Okay. And so this kind of puts us in our last use case where whenever we take a higher order derivative and we still get 0, that means we have to take another derivative. So let's take a third order derivative. Since this is 0. Let's take one more derivative. Let's take a third order derivative, d cubed f dx cubed. Okay. And so if we do that, then what we end up with is the following. So I'm going to simplify it a little bit. So I'm going to skip a couple steps, but it's the same process as before. We have 60 times 12x squared, it's 18x, it's 4. Okay. So we're going to evaluate this at x is equal to 0 because that is the extrema in question here. Okay. Because we don't know whether x is equal to 0 is a max, a min, or not. Okay. And so we evaluate this at x is equal to 0, and what we get is d cubed f dx cubed equal to 60 times 12 times 0 squared, it's 18 times 0, it's 4. This is equal to 240. And so since we got a non-zero result and our derivative order here is odd, so we're on the third order derivative. That means x is equal to 0 is neither a max nor a min, it's a saddle point. And so if we kind of plot the function will kind of flatten out a little bit, but it's not going to continue to change direction. It's going to flatten out and then kind of continue upwards. It's coming from the other way. Okay. So it's kind of something that's kind of in between. Okay, so that example was a little bit more detailed, but I think we got to see basically all three cases here. And so we got to see what a maximum looks like, what a minimum looks like, as well as a saddle point. Okay. And so this is kind of the criteria, or this is kind of the methodology that you would follow for single variable cases. All right, any questions on this example here? Okay. All right, let's do one more example. This next example here is more closely related to engineering, specifically in the realm of thermal fluids. Okay. But it's still going to be a single variable case. And so even though the terminology and the equation is going to be more complicated, we're still going to follow the exact same procedure that we just followed. Okay, so let's look at a two-stage compressor. And so if you're unfamiliar with the concept of a compressor, it basically just compresses air and it makes it higher pressure. Okay, or excuse me, lower volume. In a two-stage compressor, basically you're going to have one compressor which is going to provide the first stage of compression. Then in between the two compressors, you're going to have a cooling unit, whose goals are going to cool the gas. And the whole idea with this cooling unit is that it's meant to increase efficiency, because as you compress a gas, you know, the gas will tend to heat up because you're basically adding energy into the gas to kind of compress it, right? But as the temperature of the gas gets hotter and hotter, it becomes even more difficult to compress it. So to kind of alleviate this, engineers have come up with this two-stage design where you do a kind of a partial compression, then you move on to a cooling unit, it cools down the gas. Then you move on to the second stage of the compressor to kind of finish that compression. Okay, and so the diagram of this looks something like this. So gas is going to come in. It's going to enter kind of the first stage of the compressor right here. So this is compressor 1. It's going to leave compressor 1. It's going to come to this middle unit right here. In the middle chamber, it's going to cool the gas, and so you're basically going to run it through a refrigerator, almost, or a freezer, to kind of cool the gas. And then you're going to enter the second compressor, which is going to finish the compression process. At each stage of this process, we can characterize what the average pressure of the gas is going to be. Okay? And so in compressor 1, we have P1. In the cooling chamber, we'll call that P2. and compressor 2, we'll call that P. So P1, 2, P3, average gas pressures. At each. Okay. And so under this setup right here, we can compute the total amount of work or total amount of energy that's required to run this system using the following formula. We have work is equal to CP multiplied by T1 multiplied by ratio of P2 1 all raised to the K minus 1 divided by K power plus ratio of P3 2 raised to the K minus 1 divided by K power minus 2. Okay, so let's go ahead and label all of these symbols here. So let's start with CP. So CP here is the specific heat of the gas. We have T1. T1 here is the average temperature of the gas. Average temperature of the gas as it runs through this through this compressor. And last variable is K. And so K here is the ratios of the specific heats at constant pressure to the specific heat at constant volume. So it's a very lengthy description, but it's a very common kind of thermodynamic problem. Okay. So a little bit of a complicated setup, lots of variables. Hopefully variables you've seen before in either thermodynamics or heat transfer. Okay. So we want to optimize this process. And so generally when you have a process here, this is a very thermodynamic process. Usually what you want to do is you want to minimize the power required, minimize the work required. Okay. And so we're going to try to minimize this function. Because usually you're going to see a system like this probably in some kind of industrial application. You're compressing a lot of gas, a very large volume of gas, for some, maybe some manufacturing process or something. Okay. And if you can minimize the work required or minimize the energy, that's going to, save your company a lot of money and, be ultimately very, very good. Okay, and so we want to, based on this formula here, we want to minimize it. Okay, and the one design variable that we're going to use, or we're going to optimize over, is going to be P2. Okay? And so find. So let's find the optimal value for P2. The optimal value for P2 that minimizes the amount of work required. So we're going to assume everything else is fixed in this problem. So P1, P3 are fixed, and all the thermodynamic properties Cp, K, T1 are all fixed. All right. Any questions on the setup for the problem? All right. So we have a single variable optimization here. It's quite a bit more complicated because our expression here involves exponents. But in theory, it's still the same as before. So we're going to follow the same process, and so we're going to take derivatives, and we're going to find out, if that extrema that we find is a maximum or a minimum. Okay, so first, and so let's take a first derivative of w with respect to P2 and set it equal to 0. So we have dw dp2. And so let me write it like this first, because the derivative is going to be a little bit complicated to do. So I'm going to say ddp2 cp t1 multiplied by p2 over p1 raised to the k minus 1 k power plus P3 over P2 raised to the same exponent, k minus 1 divided by k. Okay. So we have quite the task in front of us, but if we kind of break this down kind of step by step, hopefully you'll see that's not too bad. Okay. All right, so first thing I'm going to do is, since I know that Cp and T1, both of these are constants, we're not taking derivatives with respect to these, and neither of those things depend on P2. Let's factor those out. Okay. We have Cpt1. It's just a constant multiplying the whole thing, and so when we take the derivative, we can just pop that out in front just like that. Okay. All right. Another thing I'm going to do in this step is I'm going to take this derivative and I'm going to distribute it to the 3 remaining terms. Okay. And so in the end, what we get is the following. So we have Cp T1 multiplied by derivative with respect to P2 of 2 P1 raised to the k minus 1 divided by k power. That's the first term. Then we have the second term here. Then we have derivative of 2. All this is equal to 0. Okay. So we can simplify a lot of things here. So a lot of terms are going to cancel out. First thing we're going to do is that since we know that this is all equal to 0, we're going to take the CPT1 and divide it by both sides. So we're just going to cancel out this this guy right here. Okay. Divide this out. Next, we have the derivative of a constant. So we have a derivative of 2. Okay. It doesn't matter, what we're taking the derivative of. If we take a derivative of a constant, derivative of a constant is always 0. So we can just go ahead and cancel that guy out as well. All right, so that simplifies our life quite a bit. Any questions on this so far?
So why don't you just make the exponential term constant, like make it R or N?
You could do that. So you can simplify the exponent and make it a constant, and then kind of factor that in later as well. That could simplify things as well. So that's another strategy that you can use. Yeah, because the k is a constant, there's no need to kind of keep it in that kind of stuffy form.
And P1 and P3 are in the function of P2, right?
Exactly. Right. So so next step, I'm gonna factor those out of the derivative as well, just to kind of clear things up. Yeah. Right. So next step, let's go ahead and factor out P1 and P3 from the derivatives. And let's go ahead and make that simplification too. So, since instead of working with k minus 1 over k as the exponent, since all that's a constant, let's go ahead and substitute. Let's call it a factor r. I'll say r is equal to k1 minus k minus 1 divided by k. Okay. And so if we do that, we get 1 over P1 raised to the R power is dP2 of P2 raised to the R power. Okay. Plus we have P3 raised to the R power, and that's dP2. I'm gonna do something in here just to make it a little bit easier, because we have 1 over P2 inside here, so I'm gonna do P2 raised to the negative R. Okay. So in this form, hopefully it's a little bit clear to see. And so we don't have integer exponents here, but we do have a constant, and so we can apply our normal power rule. Okay. And so we have 1 over P1 raised to the R power. Derivative of P2 raised to the R power is going to be R times P2 1 plus P3 raised to the R power multiplied by minus R. And this is going to be P2 raised to the minus R minus 1. Okay. And all this is equal to 0. All right, so from here we can use algebra, and so remember, the goal of this step is to solve for the value of P2. Okay. And so we're going to solve for that using this expression. Okay. All right, so first thing I'm going to do is we have a factor of r on both terms, and so let's go ahead and cancel that out. And then what I'm gonna do is I'm gonna take this term here and move it to the other side of the equation. And so on this, on the left-hand side, what we're gonna have is P2 minus 1 divided by P1 raised to the R is equal to P3 over P3 raised to the R divided by P2 R plus 1. Okay. So let's go ahead and perform a switcheroo. So we're going to multiply both sides by P1 over R. So I'm basically going to move this into the numerator here. And then I'm going to move this into the numerator up here. Okay. And so we have P2. And when you multiply two terms with different exponents, remember, you're going to add their exponents together. And so here we have P2 R minus 1 plus R plus 1 is equal to. And then together here we have P1, P3 raised to the R power. Okay. We simplify the exponents on the left-hand side, we get P2 raised to 2R. And on the right-hand side, we have P1, P3 to the R. Okay. All right. Since we have R's on both sides of on the exponents on both sides, what we can do is we can take the R root of both sides and kind of cancel that out. Okay. So that looks like this. Well, I think the easier thing would be to kind of raise it to the 1 over R power. And so that'll get rid of the R there. And so we have P2 squared is equal to P1, P3. So let's go ahead and just take the square root, and then we will solve for P2. So we have P2 is equal to square root P1 P. It's quite a lot of work, but you know, I think that suggestion helped a lot to use R instead of K minus 1 over K. All right, any questions on how we obtain this result here? Okay. All right, so this is good. So we have a value for P2, and so we know the work has an extrema at this location, but we don't know whether it's a maximum, a minimum, or it could be neither, right? And so this is an extreme. So the next step is to take another derivative to determine whether this is a maximum, minimum, or. Okay. Because it would be pretty bad if this were a maximum, right? And so if we set C2 equal to this, then if that maximizes the amount of work, then that's bad, right? We don't want to maximize our work, we want to minimize it. Okay. Okay, so let's take another derivative. And so we're gonna take our expression for the derivative, and so we're gonna remember, we're gonna start with this one. Well, we don't have a convenient place to start. But I'll go ahead and give you the result here. And so just for the sake of time, just because I want to make sure I get to some multivariable optimization today, and at least start the next example, I'll say that, this is after some steps. Okay. And so skipping some of the math, the second order derivative here is going to be CPT1 multiplied by 1 over P1, the R power, times R minus 1 P2 2 plus 3 R minus plus 1 excuse me, plus R minus R. P2 minus R. I have to check that. I'm trying to plug in R kind of in real time, because what I have in my notes is everything in terms of K. All right, but if you take this expression here and you plug in if you take this expression here and plug in P2 is equal to square root P1 times P3, okay, what you're going to get is a positive number. And we know that, because our current derivative order here is 2, and so we are at an even order derivative. And since we got a positive number, this means that our value for P2 is a minimum. So that's good. So that means we're not maximizing our work, we're minimizing. And so if you're designing this system, you want to make sure that the value for P2, which is the pressure of the gas inside the cooling chamber, is the square root of the product of P1 and P3. All right, any questions on this example here? Okay. All right, and so that's it for single variable optimization. And so single variable, algebra and calculus kind of withstanding, is fairly simple in concept. So you're basically just taking derivatives of your function, you're setting the first derivative equal to 0, and then kind of going from there. Okay. I think any difficulty that you have with these problems is due to either lengthy algebra or lengthy derivative taking, as you can kind of see from the screen. Okay. All right, so let's go to multivariable optimization. So we're going to do multivariable unconstrained optimization. And remember, we're still using the classical approach. And so even in multiple variables, we're still going to be taking derivatives. It's just that, since we have more than one variable, we're going to take multiple derivatives. And so we're going to look at cases with multiple design variables. So now our objective function will have more than just one x, and so it'll be x1, x2. We're not going to get beyond 2 because these methods kind of the work required for these methods kind of scales up pretty hard. But in theory, you could apply these methods to 3 variables, 4 variables, 5. As many as you want, as much as you have patience for the algorithm. Okay. And so even though we're working in multiple dimensions, multiple variables now, our approach is still the same. It's just that they have to be modified slightly for it to work in multiple dimensions. So just like in the 1D case, we're going to have 2 criteria or 2 steps that we're going to follow to find out the extreme. Okay, so step 1. And so remember, for our single variable case, our first step was to take the first derivative of our objective function and set it equal to 0, right? We're going to do the same thing here, except we're going to have multiple first derivatives because we have multiple design variables. Okay. And so we're going to take all the first partial derivatives of the objective function, and the number of partial derivatives that we're going to have equals the number of design variables, and we're going to set them all equal to 0. Okay. Okay. And so mathematically, it's going to look like this, and I'm going to use partial derivative notation here because we're in a multi-dimensional case. We have partial f1 or partial x1 is equal to 0. Okay. Partial x2 is equal to 0. And this is going to continue until you run out of design variables. So it's going to all go all the way to partial f, partial xn is equal to 0. As a reminder, I use little n. I'm going to use this symbol throughout the entire class. N denotes the number of design variables that we have. All right, so of course, since we're taking multiple first order derivatives here, we're gonna get in the end is multiple equations, okay? And so we need to solve those equations simultaneously in order to solve for the values of x1 through n. And remember, just like in the one-dimensional case, you may get multiple sets. And so sometimes you may just get one set. So you may just get one set of x1 through n, and that may be the only extrema for your function, okay? But sometimes you might get multiple, and so you might get multiple extrema, just like you do in the 1D case. And then you can check whether they're a max or min using the next step, okay? But the important thing is that, this step, I think, suddenly becomes a little bit harder because instead of solving one equation for x, you're solving multiple equations at the same time for, multiple values of x. Okay. All right, so that's step one. So step one, mostly the same as the 1D case, it's just you got to do more work, because it's in multiple dimensions. Okay. Step two here, it looks a little bit different. The concept is the same. And so we're going to take a higher order derivative, but how we organize it is a little bit different because we're in multiple dimensions, okay? All right, so in step two here, we're going to compute something called the Hessian matrix. And I know, for those of you who have seen this before, I know people call it the Hessian. I pronounce it like an American. So I'm like reading this just purely as it is. So I call it the Hessian, but you'll probably hear people call it the Hessian sometimes as well. Okay. And so if you've never seen this before, the Hessian matrix is a matrix of second order partial derivatives. It's a square matrix, second order partial derivatives. And then based on the characteristics of the Hessian matrix, we can determine whether the extrema that we found in part one is either a max, a min, or right, so there's a couple of things here. So, first of all, we have to learn how to actually compute the Hessian matrix, which we'll do first, and then next we'll talk about how you can tell from the Hessian matrix, whether you have a max, a min, or saddle. Let me just pause here for a second though. Are there any questions on this so far? Okay. All right, so let's go ahead and let's learn how to compute the Hessian matrix. So the Hessian matrix, usually I give it the symbol capital H. Okay. In index notation, it looks like the following. So you have partial squared f, partial xi, partial xj. Okay. And so this I and this j are very crucial. So these I and j refer to the rows and columns of the square matrix. Okay. So I here refers to the row, and the j here refers to the column. Okay. And so remember, when you're taking second order derivatives with in multiple dimensions, you can take different combinations of derivatives of the different variables. Okay. And so you're going to see some cross derivatives in this matrix. Let's see what it looks like. All right. And so the way to kind of interpret this is to kind of set the values of I and j equal to the values of whatever row and column that you're in. Okay. And so in the top left entry, this one right here, okay, we're going to be at row 1 and column 1 of the matrix. So that means I is equal to 1 and j is equal to 1. And so this is going to be partial squared f, partial x1 squared. Let's go one entry to the right. And so if we go one entry to the right, we're in row 1, okay, we're still in the first row of the matrix, but we moved on to column 2. Okay, so this is row 1, column 2. Okay. So that means I is equal to 1 and j is equal to 2. And so this is going to be partial squared f, partial x1, partial x2. Okay. So we have a cross derivative. We can kind of continue that trend down, down the length of this row. So we have partial squared f, x1, 3, okay. And this is going to continue until you reach the n, which is the number of your design variables. Okay? And so the last entry in this row is going to be partial squared f, partial x1, partial x n. Okay, so let's go to the next row. And so if we go to the next row, we're going to be in row 2. Okay? And if we're looking at the very first column right there, it's going to be column 1. And so we're going to have partial squared f, partial x2, partial x1. So one thing to note about the Hessian matrix, and one good way that you can check your result, is that it should be symmetric. Okay. And so it doesn't matter if we take the derivative with respect to x2 before x1. Okay. These two entries right here should be identical. We have partial squared f, partial x1, partial x2. And then we have the same thing here, except we take the x2 derivative first, then x1. Okay. So it should be a symmetric matrix. And so if you go down the diagonal, right, you should see kind of a mirror image of the matrix on both sides of that main diagonal. Okay. Right. So then we go to the next entry. So that's row 2, column 2. So that's partial squared f, partial x2 squared. Squared f, x2, partial x3. Continue this down, we have partial squared f, x2, partial x n. Okay. So hopefully you guys are seeing the pattern now. Right, so I'm just going to write out kind of the generic terms from here. So we go down all the way to the bottom. So the last row in the matrix will have partial squared f, partial xn, x1. Okay. We'll continue everything until the very bottom right. In the very bottom right, we have partial squared f, partial xn. Okay. So I think this form, I think when people see something like this, I think they get intimidated a little bit just because there's a lot of symbols and a lot of things like that. But this is kind of the most generic form for the Hessian for the case of any number of design variables. Okay. But most commonly in this class, we're going to work on either 2 or 3D cases, mostly 2D, just because it kind of gets unruly from there. And so let me show you the Hessian matrix for a two-dimensional system. So luckily for a 2D system, we only have a 2 by 2 Hessian matrix. We have A to the 2, partial squared f, x1 squared, partial squared f, partial x1, partial x2, partial squared f, x1, partial x2, partial squared f, partial x2 squared. And that's the one I'm going to use for the exam that we won't get to today, but we will on Thursday. Okay. Any questions on the Hessian matrix so far and how we compute it? Okay. All right. And so, how do we use this Hessian matrix to determine whether we have a maximum or minimum or a saddle point for our optimization? Okay. And so once we've computed the Hessian matrix, we have to check if the Hessian is positive definite. Okay. And so if the Hessian is positive definite, and I'll define what that means in a second, then the extrema that we found is a minimum. Let me find Thursday, just about out of time. If the Hessian is negative definite, then the extrema is a maxima. We have positive definite, negative definite. Okay. If you're in between these two, we usually call it semi-definite. And so in that case, technically speaking, you need to do more work. But for the cases that we're going to look at in this class, if your Hessian is semi-definite, we're going to say that you have a saddle. Okay. So unfortunately, we won't be able to get to the definitions of positive definite, negative definite, but we're gonna start the lecture on Thursday with those things, okay? And so we'll go ahead and define those on Thursday. We'll do a couple of examples that kind of illustrate this process, okay? And then we'll be done with the unconstrained optimization. All right, any questions on this before we wrap it up for today? Okay, all right, so we did a lot of math today, but hopefully the examples we did today were useful, right? And so with that, you should be able to do everything on homework 1, because homework 1 only covers up to single variable optimization. And so definitely give that a try. If you have questions on the homework, I do have office hours tomorrow in the evening from 5:30 to 6:30. Okay. Or of course you can ask me questions in the lecture on Thursday as well. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Trevor, any final questions before I wrap it up? See you Thursday.